Hey everyone, welcome back to this video with Rethink Education. Today we will be discussing work and energy part 2. So we're going to take a specific look at the kinetic energy of an object, the conservation of energy, and then the conservation of mechanical energy. And we're going to have a look at how to deal with problems that relate to these. Before we dive in, let's just do a quick recap on what we discussed in the last video. We know that work is done on an object when a force moves the object in the direction of the force. Work is equal to force times displacement times cos of theta. And we also know that work is a scalar quantity and therefore we only worry about its magnitude. Energy is the ability to do work and it is measured in joules. It is also a scalar quantity, and specifically potential energy is the energy that an object has due to its height above the ground. EP is equal to mass times gravitational acceleration times height above the ground. Great, so now we can move on and take a look at kinetic energy. This is the energy that an object possesses by virtue of being in motion. Now all that's saying is that if an object is moving, then it has energy, guaranteed. We can quickly derive this formula again from the work is equal to force times displacement formula, because we know that if a resultant force acts on an object, then the object will accelerate from Newton's second law of motion. F res is equal to ma. We therefore get work is equal to mass times acceleration times displacement, but we know work is actually energy. So let's call this kinetic energy, or EK. Therefore, EK is equal to mass times acceleration times displacement. But from the equations of motion, we get V final squared minus V initial squared is equal to 2AS, or 2A acceleration times displacement. And therefore, if we compare this against the zero initial velocity, so if we look at the final velocity as compared to the initial velocity being zero, then we get v squared is equal to 2as, and so we can conclude that EK is equal to a half mv squared. Now you really don't have to stress if you don't quite understand that derivation. You're never going to actually have to know it for a test, but it's some good practice to understand to make sure that your physics is up to scratch. So run over the math slowly and see that all the steps make sense to you. I've written it out in full, so you can play that over slowly and make sure that it all makes sense to you. So this brings us quite neatly to the mechanical energy topic. Now, mechanical energy is simply the combination of potential energy and kinetic energy. Therefore, if an object's potential energy is 20 joules, we know firstly it has to be above the ground. And if it is not moving, then we also know its kinetic energy has to be zero. Then its mechanical energy, which is the potential energy plus the kinetic energy, is equal to just the potential energy is equal to 20 joules. We could also look at an object that is on the ground. It therefore has a potential energy of 0 joules because its height is 0. But if it is moving with an EK of 20 joules, then its mechanical energy is equal to 20 joules. So let's have a look at an object that's now above the ground and has an EP of, let's say, 20 joules, and it is moving, and let's say it has an EK of 20 joules, then we know its mechanical energy is equal to 40 joules. So it's pretty straightforward, right? You'll see just now why that's actually so important. But what we're trying to do is we're aiming towards the conservation of mechanical energy as a total. But to get there, we actually need to look at the conservation of energy as a whole. Now, the law of conservation of energy states that energy can neither be created nor destroyed. It can only be transformed from one form to the next. Now, this is saying that there is only so much energy to go around, and we can only make use of it by actually changing it into different forms. A common example of this would be burning coal to boil water, to then turn a turbine to generate electricity, and finally that electricity can be used to generate heat to cook on or generate light in a light bulb. There are hundreds of different applications of this electricity. I'm sure you can think of some more by yourself, but we therefore know that this energy doesn't magically appear. It was stored in the coal originally, and we simply harnessed it to change it into a form that is useful to us. Now, this law holds for mechanical energy of an object as well. We can state that if a conservative force does work on an object, then the total mechanical energy of the object remains constant throughout the movement. This means that the energy won't be lost, it will simply be changed in its form. So now there is one piece of the definition that we don't yet understand, and it's the part dealing with the conservative force. I looked it up on Wikipedia and got a conservative force is a force with the property that the work done in moving a particle between 2 points is independent of the path taken. You should have already worked through the explanation of exactly why gravity is a conservative force, so I won't dwell on this too much. Just very quickly, we can take two paths for an object to move over a certain displacement. Now, just remember that we are now talking in the vertical plane. So we get path 1 and path 2. You can see them there. We can calculate the work on each leg of the different movements as follows, and we can clearly see that the work that gravity does on the object is independent of the path that it follows. For that matter, we can take any path whatsoever as long as we end up at the same ending point, then gravity does exactly the same work on the object always. A non-conservative force, such as friction, does not have this property of path independence. Therefore, the work that it does on an object will now depend on the path that it followed. Again, we can demonstrate this with the following quick example. Imagine you push a box and you're trying to move it into the corner of a room. You have to push it around a couch, and the frictional force that is encountered along the way is a constant 5 newtons. So we're not going to bother with the kinetic coefficient of friction this time. Let's just take that as a constant. If we push the box this way and then calculate the total work done by the object, we get it to be minus 13 newton meters, and if we push it this way, then we can see that the work now done is minus 25 newton meters. These are clearly different, but the question is why? What made gravity and friction different? Now, the difference comes in how friction changes depending on what the object is doing. It will always be opposite to the object's movement, and therefore will always cause this negative work to happen. Gravity, on the other hand, doesn't really care what the object's doing. It will always pull the object towards the center of the earth with a force that's equal to the object's weight, and this never changes. It doesn't matter what happens to that object, it's always going to be pulling towards the center of the earth. And that's exactly where the difference lies. So the conservative force will only cause the object to have its energy change in form. The non-conservative force will actually result in the object changing its energy, but remember that this energy is not lost in the greater sense. It is converted to heat or sound or some other form that is actually just inaccessible to the object. Alright, well, thanks for bearing with me for that one, but it's quite an important term to come to terms with. So we can now move on and really delve into the conservation of mechanical energy. You will mainly deal with objects that have their kinetic energy changed to potential energy and vice versa, and therefore it is the movement under the influence of gravity that we need to study. We have just learned that mechanical energy is conserved if the force acting on it is conservative, and we know that gravity is conservative, so we're all good. Therefore, if we look at a quick example, if an object is sitting at the top of a cliff and it drops off the cliff, we know that it started with a potential energy of, let's say, J joules. We also know that the mechanical energy was equal to the potential energy, as the kinetic energy was 0 joules. The object wasn't moving at the top. But then as the object falls, its potential energy is now transferred into kinetic energy, and eventually, just before it touches the ground, when its height is actually 0 meters, then the kinetic energy is now equal to the total mechanical energy, and therefore it is equal to J joules. It is worth noting that again, the path the object takes does not matter. Why? Because we are dealing with the conservative force of gravity. Nice, eh? So if the object slides down a ramp instead of falling off the cliff, it still starts off with the same potential energy, and it still converts all of its potential energy to kinetic energy. The mechanical energy is equal to the potential energy at the top, and as long as there's no friction present, all of this mechanical energy is equal to the kinetic energy at the bottom, and that kinetic energy at the bottom is therefore still equal to the potential energy at the top. We can do the same thing in the other direction. If an object with a mass of 2 kilograms is thrown up with a velocity of 3 meters per second, then what is the maximum height that it can reach? We know that the mechanical energy at the bottom equals the kinetic energy, and the potential energy is equal to 0 joules as it's at a height of 0 meters. We can therefore calculate the kinetic energy and therefore the mechanical energy to be 9 joules. We also know that the mechanical energy at the top of its movement is equal to purely its potential energy, as the object is now not moving when it reaches the peak of its movement. Therefore, its potential energy, or EP, is equal to 9 joules, and so mgh is equal to 9 joules, and the height can now be solved to be 0.459 meters above the ground. Okay, so that's it. We dealt with quite a few pretty important concepts very quickly in the video today, so make sure that you're 100% happy with what we have discussed. Watch the video again to cement the ideas and work through the content in the rethink discussion to really get a grip of it. Remember that mechanical energy is the sum of potential and the kinetic energy, and that is only conserved if the force causing the work done on the object is a conservative force. We can now also note that a non-conservative force will change the magnitude of the mechanical energy, and a conservative force will only change the kinetic energy to potential energy, or the other way around. I'll see you guys in the next one. Thanks for listening. Cheers.